On March 23, 2005, an explosion occurred at the Texas City BP petroleum refinery plant. 15 people died as a result of this explosion and more than 180 people were injured. Windows as far as 4,000 feet away from the explosion were shattered from the blast, resulting in significant economic losses. The incident is considered to be one of the most serious workplace disasters in the past 3 decades. Incidents like this remind us why it's important to practice inherently safe design and to keep up with regular maintenance of process equipment. We'll look at what happened at the Texas City, Texas plant and determine what could have been done to prevent such a disaster from occurring. But first, let's define some terms. You may be asking, what is inherently safe design? It contains 4 principles: minimize, substitute, moderate, and simple. Minimize involves reducing the amount of hazardous substance in a process. Rather than having large amounts of toxic or flammable materials that could be released into the atmosphere and cause harm, it is much safer, if possible, to reduce their amounts to levels that would not be as dangerous if an accident did occur. If a reaction calls for a highly toxic or potentially destructive chemical, it is in everyone's best interest to see if there is another, safer alternative that can perform the same task without the same risk. This is the idea behind substitution. Moderate is the idea of using milder conditions. If a reaction is being operated close to a temperature or pressure that could cause a runaway reaction, it's best to consider other conditions that the reaction could operate at, even if those conditions result in a reduced yield. If a system or set of controls are difficult to operate or understand, the possibility for an error to occur increases. Simplifying the system so that it's easier to operate and understand will reduce the chances of an error occurring. Now let's take a look at what exactly happened at the Texas City BP plant. Here is a map of the Texas City BP petroleum refinery plant. This map includes the splitter tower and the blowdown drum. Notice there are some trailers placed very close to the plant. 2:15 a.m., operators began filling a splitter tower. It was common practice for operators to deviate from the recommended liquid level of 7 feet indicated by the level indicator, which is designed to measure levels between 5 to 9 feet, during startup to avoid the possibility of a low liquid level causing furnace damage. 3:09 a.m. When fluid in the tower reaches 7.6 feet in the tower, the high-level alarm sounds but is ignored. The redundant high-level alarm switch does not sound when the tower level reaches 7.9 feet. 3:30 a.m. The tower is filled to what the operators believe to be 9 feet, when in reality the tower was filled to 13.3 feet. 5 a.m. Lead operator and satellite ISOM control room give briefing to Central Control Room, the CCR, and leaves to go home early. 6 a.m. New CCR operator arrives to start his 30th consecutive day doing 12-hour shifts. Shift log contained a 1-sentence logbook entry about the level and state of unit during startup. That occurred early in the morning. Shift log entry read, ISOM unit, brought in some RAF to unit. 7:15 a.m. The day supervisor arrived late and missed handover briefing with the night shift lead operator. 9:51 a.m. As a result of lack of communication, the day supervisor resumed the startup by recirculating the liquid feed, increasing the liquid level in the tower. The operators left the auto level control valve at the bottom of the tower closed due to conflicting instructions of when the valve should have been controlled to maintain a safe liquid level in the tower. 10:47 a.m. The day supervisor left in the middle of the startup procedure for a family medical emergency without notice, violating BP's procedure of assigning a substitute supervisor in the CCR during his time away, leaving one control operator around 3 units, with one of them being in the ISOM unit during the startup, which required close attention. 11:16 a.m. 2 additional burners are lit while the level in the tank is reported as 8.65 feet. The actual level is close to 67 feet. 11:50 p.m. The level in the tower reaches 98 feet. Due to poor positioning of information on the operator's control screens, he was unable to clearly tell that the flow into the tower was higher than the flow out of the tower. 12:41 p.m. An alarm from the tower indicated high pressure in the tower, prompting the operators to manually open the vent valve to vent gases into an old blowdown drum, which is vented off combustible gas to the atmosphere. Operators turned off 2 burners in the furnace to reduce the pressure. They then opened the outlet valve to send liquid from the bottom of the tower into storage tanks. However, the liquid leaving the tower was extremely hot and flowed through a heat exchanger designed to heat the feed to the tower thereby continuing to heat up the feed entering the tower. The hot feed caused the liquid inside the tower to boil over, resulting in the liquid to spill over into the overhead vapor line and exerting great pressure on the emergency relief valve 150 feet below. This caused the relief valves to open and send 52,000 gallons of hot liquid to the blowdown drum. The liquid inside the blowdown drum rose far enough to begin draining into the process sewer system, setting off a second alarm in the control room. Another high-level alarm in the blowdown drum failed to go off as the hot liquid level continued to rise to the top of the blowdown drum, causing a mixture of flammable vapor and liquid to erupt from the top of the blowdown drum. This formed a huge vapor cloud that expanded in 90 seconds, enough to engulf the ISOM unit and the nearby trailers that the maintenance workers occupied. 1:20 p.m., an idling truck engine nearby ignited the vapor cloud, causing a huge explosion. The pressure wave from the blast caused significant damage to the ISOM unit and resulted in fires that burned for hours. The explosion killed 12 of 20 occupants in the trailers and 3 others in different trailers, and destroyed multiple other trailers and nearby structures. Dozens suffered serious burns, fractures, and other traumatic injuries. 50 large chemical storage tanks were damaged. The ISOM unit remained shut down for 2 years. Inherent safety shortcomings include that the blowdown drum was undersized, causing liquid release from the top of the ISOM blowdown stack. Also, the blowdown drum was not connected to a safe disposal system, such as a flare to safely contain discharged liquid in a disposal drum and burn flammable vapor, preventing a hazardous release to atmosphere. And finally, there was no established minimum safe distance for the trailers and similar temporary structures away from hazardous areas of process plants. Finally, computers were not configured to read instrumentation clearly. Red flags for this incident include minimizing capacity of the ISOM unit. Level indicators should have been able to measure the true liquid level inside the tower and not a maximum of 9 feet. BP had not completed a relief valve and disposal collection piping study for the ISOM unit, which was necessary to determine if the drum was adequately sized. Trailers have been periodically sited in and around hazardous process areas for reasons of convenience, such as ready access to work areas. Key alarms and level transmitter failed to operate properly and to warn operators of unsafe and abnormal conditions in the ISOM unit. Written startup procedures for the raffinate splitter were incomplete. Texas City Refinery experienced 2 fatal safety incidents in 2004 and serious furnace fire. BP pre-startup safety review, which included complete and thorough technical checks as well as clearing all non-essential personnel, were cleared during the startup operation, requiring refinery operation and safety manager's approval, was not completed. Thanks for watching. I hope you learned something out of this video. If you did, like and subscribe to our channel. We dearly appreciate it. Thanks.